Okay, Chem Scholars. Today we're going to kind of review something that, again, was also in Unit 1. So you see how the AP is kind of overlapping things, having them cycle back around. So Section 2.3 is about structure of ionic solids. I'm also going to go into alloys because they're both small topics, really very minimally covered in the AP exam. And so that's the approach that we're going to take. So, with that said, we got into the idea of ionic compounds and the idea of a lattice, of a regular repeating structure. You look at the pattern here and you see, this gray is bonded not to just one green, but really it's bonded to 5 different greens because there's one behind it and 4 alongside of it, and so on and so forth. So what makes ionic compounds so special is this lattice, but also the way that it's equally attracted to multiple things. This, this cation, this sodium ion, is equally attracted to this chloride, this chloride, this chloride, this chloride, and the one behind it, and so forth. And I could say the same thing for this chloride between this sodium, this sodium, this sodium, this sodium, and the sodium behind it. And obviously, if I took one out of the middle, it'd probably have 6 ions surrounding it. See if I can't show you that. So, for example, this blue one in here, okay, has 1, 2, 3, 4 chlorines, 5, 6 chlorines that it's attached to. Okay, so that's what we're talking about. And we went through these properties the other day. I'm not going to go through them again. We've talked about the whole basic idea of ionic compounds already. It's really, the emphasis is about this repeating structure. Okay, that's really the gist. We talked about lattice energy, and it's how much energy is needed to break up the atoms into gaseous ions. I'm sorry, not the atoms. Break up the ionic solid into gaseous ions. We talked about the fact that charge comes first. You always look at the charge and see if it has a bigger charge, it's going to require more lattice energy. And then size becomes a secondary issue. If it is smaller, it will require more lattice energy because being a smaller atom means that the electrons are going to be closer to the nucleus. And so that means that, electrically speaking, smaller atoms will get closer to one another and have a stronger attraction. Again, we talked about the table and the idea that, when we compare lithium fluoride, lithium chloride, lithium bromide, lithium iodide, you see that the size of the fluoride, chloride, bromide, iodide are increasing. The lattice energy is decreasing. But now when I throw in a -2 charge, lithium oxide, now all of a sudden the lattice energy jumps significantly. Okay, that's why charge comes first. Okay, I mean, look at this chart. If we go down to aluminum oxide, that's a huge number compared to anything else on the table. Because of the fact that we have +3 and -2, we have bigger charges. All right, so let's jump into this topic of alloys. So what is an alloy? An alloy is essentially kind of like a solution, but it's not quite completely homogeneous. Okay, it's a mixture in which elements are added to a metal, okay, to alter the properties of metal. It happens all the time. You think of history, there was the Bronze Age. Okay, well, bronze was made because the copper weapons that they were using just weren't too malleable. They needed something to give it a little bit more substance, so they started adding tin in there. And so, that's where the idea of an alloy starts coming in. They start mixing in different things to try and see. And nowadays, we do so much with steel, and there's so many different types of steel because we take the iron and we mix in a little bit of carbon and maybe a little bit of tungsten or a little bit of molybdenum, and each of those is going to bring in a new set of properties that will allow this to mix and form essentially a new metal, but it's not really a true metal. Metals are just elements. It's metallic. It's an alloy. There are primarily 2 classes of alloys. There's substitutional and interstitial, but you'll see in the picture here that you can have both, substitutional and interstitial. Okay, Substitute means literally we're taking an atom out, plugging something else in. So looking at the pure metal, you see as we come here, we take out one of these atoms, we plug in one of the new atoms. By comparison, the interstitial, you see it gets in between. And the biggest difference is about the size. And when you're putting something in of roughly the same size as the metal that you're starting with, it's going to have to be substitutional because it's not going to fit in the gaps. But if you're putting something smaller in, then it will fit in the gaps. So that's really what we're looking at in these alloys. So I mentioned steel. Okay, one of the most common things that's added to steel is carbon, sometimes boron. I've never seen nitrogen, but I'm sure it happens. But when it's an interstitial, it's got to be small atoms, and nonmetals tend to be small atoms. So it makes sense that these substances, being some of the smaller ones, would be the ones that would plop into there. They just kind of fill in the holes inside of the metallic substance, but it's going to alter the properties because carbon, being a nonmetal, is not going to be as malleable as iron, and so on. Whereas a substitutional, here's an example of 14-karat gold. Okay, what we see is, the gold atoms are a little bit bigger than the silver atoms, but not hugely different in size. And so what we get is a little mixing of properties. Okay? It doesn't turn out to be quite the same color, and it changes the malleability of it a little bit and all. Obviously, it changes the cost factor of it a bit. So you still have a gold-ish look without it being quite as expensive as if it was pure gold, which is 24-karat gold. So it's really, this idea of substituting in there, and we get this effectively like a covalent bonding going on with the different atoms in our alloy. And so that's really all you need to know for this subsection, is just understanding what substitutional and interstitial alloys are. So I'm going to stop it right there. That's 2 sections down in a heartbeat. Bam.